I was attending an event a couple of months ago, and one of the speakers, at the end of his talk, he was trying to encourage us to follow our passions. And to do that, the question he was asking was, which is the very first thing you want to do every morning just right after waking up? Well, I'll be honest and say that is to kiss my husband and have a good toast for breakfast. But the truth is that every morning I am very much willing to go to work. Already as a kid, my favorite toy was a microscope, and I could spend hours observing the wings of different bugs or my own blood through the lenses. And nowadays, I still enjoy every day surrounded by science and by microscopes, but now with a completely different purpose. Probably everyone in the room has heard the number of challenges that our society faces. We all have heard about pollution. We all have heard about global warming. We all have heard about the challenge of satisfying our high energy demands in a sustainable way. I remember I became aware of what pollution implies for the first time when I was 12 years old. I was in a family trip to London, and what we would see there was something similar to this. And I found it very shocking. Look at that sky. And the picture we see now is recent, but what I saw was almost 20 years ago. And this is just the visible part of it, because next to it, we have, for example, global warming. One of the main causes of air pollution is the combustion of coal and natural gas that we use to produce most of the energy we consume. In this sense, one of the fields which could help us to tackle some of these environmental challenges, like, for example, global warming, would be gas separation. And how could something that sounds so awkward possibly help us? Well, air is a mixture of molecules of different gases. What we can do is to remove or to capture those gases that we don't want to be there. Now, this is not an easy task. Gas molecules are very small. They are more than 100,000 times smaller than the diameter of a hair. And indeed, gas separation can be very energy intensive and thus very costly. For instance, some studies estimate that the increase in the electricity bill would be 80% if we remove CO2 upon electricity production using traditional means, using traditional methods. But since gas molecules have different sizes, what if we could filter them? This would be less energy intensive, since this could be achieved using membranes, so only certain gas molecules could pass through. But how to do that? How to filter our gas molecules? How to filter our tiny gas molecules? Well, now I would like you to imagine a sponge. Imagine that the holes of the sponge are perfectly ordered, and that these holes are very small. They have the sizes of different molecules. Good news, these sponges, these materials already exist. They are nanostructured porous materials, and they have fascinating properties. But how? Why nanostructured porous materials? Well, nanostructure because they are perfectly ordered, they are perfectly structured at the nanoscale, which is quite impressive, taking into account that 1 nanometer is 1 million times smaller than the tip of a pen. And porous, because as it happens in our sponge, they have holes. And because these materials have very small, very well-ordered pores, very small holes, we can use them as a molecular sieve. What this means is that here we have our filter of molecules. And what I have just described is just the tip of the iceberg. is just a small part of the beauty of these materials, and a small part of the things that we can do with them. You may have never heard about nanostructured porous materials, but the truth is that to some extent, they define the world we live in. For example, they can be a catalyst in your car to prevent NOx emissions, which causes smog and acid rain. Or you can even have some at your home, since they are used as an additive in different detergents. However, there is one problem we are still working on. We haven't figured out yet how to process them into many different desired objects. Processability is key in material science. For example, plastics have been so successful in the 20th century, among other reasons, because they can be processed into millions of different shapes. And this, we cannot do with the traditional tools we have in the case of nanostructured porous materials. And if processing them into many different objects is difficult, designing those objects is even more challenging. And this design can be very important, as we can learn from the best source of inspiration, nature. For instance, take as an example bone. Bones are made of two different materials with no so impressive properties. But since their design is perfectly ordered from the nano to the macro level, we obtain an extraordinary compound, an extraordinary material. This design is so important that is basically one of the reasons why we are able to walk. So bones can be 3D printed for biomedical applications. So what if we could also use 3D printing in order to process our porous materials, our star technology of the 21st century? Well, imagine that in a similar way to the bone, we could take our porous material, already structured at the nanoscale, and design it in a wider range, from the holes to the macro scale. Well, then the scenario would be different, and we could fully exploit and use the properties of these compounds. And also, then, we could also process them into more efficient membranes. What this means is that we could take our porous material, process it into, for example, a membrane, and then use this membrane to remove the gases that we don't want to be in our atmosphere. And then, well, the view of London could be a little bit different. We could be a little bit closer to a cleaner atmosphere. And not only that, we could also be closer to a more efficient use of the resources we have. So let's follow our passions. I do it every day, and I'm glad I do it, because tiny things can solve big problems. Thank you.